Hello and welcome. With this lecture, we're going to sort of conclude the course. So I'm going to quickly summarize all that we have done in all the previous weeks of this particular course of looking at linear algebra and how it's used in practice. Okay. So first is the notion of vectors and vector spaces. So we began with that notion. In fact, we saw the example in R2, right, the two-dimensional real space in quite some detail, but nevertheless that led to an definition of a notion of a vector, an idea, and we were eventually able to extend it to so many other things. So today I think a good way to view vectors is basically any mathematical object. It could be an array, it could be a function, it could be a signal, it could be so many things. As long as you can add two vectors, two of these objects, or as long as you can scale one of these objects with a scalar, you can start thinking about it in your head like a vector. So you can do linear combinations, you can do, you can think of so many linear algebraic ideas once you have vectors making a vector space. The linear combination is sort of a central operation you should be able to perform on vectors. Okay, so this whole bunch of examples I spoke about, polynomials, signals, matrices, operators, all of these can be thought of as vectors in turn, right? Because you can add them, you can scale them. Okay, so you have to check some of the basic conditions. There are these basic axioms that make a collection of things a vector space, collection of vectors into a vector space. The addition needs to satisfy some properties, the multiplication needs to distribute, etc. Associativity, all these properties are there. The origin needs to be there. All of those properties have to be satisfied, and you can check those, but we didn't emphasize those ideas clearly in this course. Maybe if you take a future course, you can look out for this generalization. Okay, so here is the central idea, right? Operationally, what makes the basic thing that you do with vectors is linear combinations. Okay, so this leads to this idea of span of a set of vectors. You have a finite set of vectors, and if you do linear combinations with them, you can span a big subspace. And in that big subspace, you can think of basis, you can think of dimension. This is notion of linearly independent set of vectors in that subspace. So this gives you a convenient small way sort of to address this big set of vectors through this linear combination and basis and coordinates for a vector over a basis. So that's why any vector space, any vector, it always breaks down eventually into a set of coordinates over a basis. But this way of thinking about it is very, very important. It's a basic fundamental idea in this thing. Now there are specific methods. One of the methods that's very important is Gaussian elimination. And how, when you have a set of vectors, you can do this elimination process to simplify them to have a very basic coordinate system where there's lots of zeros and ones, and this leads to solving linear equations efficiently and so many other ways of manipulating equations and vectors together. So this is a very important method that you have to have comfort with. Basically, you should be able to solve a set of linear equations. Okay, that you should be able to do. Of course, you can use a computer for it today. Nevertheless, you should understand how the computer is trying to solve it. Okay, so this is the basic idea of vectors and vector spaces, the very basic operations that you should be comfortable with. The next comes the very important topic of linear transformations and operators. Instead of just dealing with vectors and addition and linear combinations, you can start thinking of mappings, functions from a vector to a vector, which preserves the linear combinations in a certain way. Okay, so those are called linear transformations. If you go from the vector space to itself, it's called a linear operator. Okay, so now this operators and transformations respect and preserve the linear combination. As in, if you have two vectors v1, v2, you do a linear combination first, like av1 plus bv2, then apply this transform. What you get is the same as applying the transform to v1, v2 individually and then doing the linear combination at v1 plus bt v2. If these two are the same, then you're doing a linear transformation. You're preserving the linearity in some way. Okay, so operators are a special case there, and it's not an exaggeration to say more than the vectors themselves. What you really study in vector spaces and linear algebra is operators. So operators, the more you understand about operators, the more they tell you about the vector space itself and the structure, what you can do, what you cannot do, what is easy, what is difficult, and all of that. Okay, so to make working with the operators very easy, just like working with vectors is easy when you have coordinates, right? When you have a basis and express it as a coordinates, it's easy to work with operators when you have basis established and you work with matrices. Okay, So that is something that we did. We saw that you can write it as a matrix, even linear transformations you can write as a matrix. Okay. So that leads to this very interesting notion of eigenvalues and eigenvectors, right? So that's sort of the next step. Once you have an operator, particularly for operators, you see that, that there are subspaces that are not altered by the operator. So instead of just seeing the linear transformation linear operator as mapping one vector to another vector, just studying like that, you look at an entire subspace. What happens to an entire subspace when a linear operator acts on it? It will generally go to another subspace. But there are these interesting subspaces which are unaltered by the linear operator, and those are the eigenspaces. And if operators have eigenspaces, then they are very, very easy to study in some sense. You get a much deeper understanding. You can work with them so much easier. Okay, so that leads to eigenvalues and eigenvectors. There are very important methods here. Once you have operators, lots of methods come in: matrix addition, multiplication, the algebra with matrices, inverse of a matrix, when does it exist, when does it not exist, all these fundamental subspaces around an operator, right? The null space, the range space, the connection between them. Once you have a matrix, you have the left null space and the left range space, the row space, so to speak, connection between the dimension of the row space and column space. So many results are there in matrix algebra and the spaces associated with matrices. Once you have eigenvalues, eigenvectors, you can understand the operator much, much better. You can do this change of basis. You can change to the basis which has a lot of eigenvectors, and what you're doing as an operator is just a scaling of coordinates, right? The scaling of coordinates is the easiest operator, so that leads to this idea of diagonalizability, upper triangularization. All the operators have an upper triangular matrix representation. We've seen that some of the operators are diagonalizable, and the diagonalizability has some conditions and all of that. So all of these methods are also important to understand. Once again, you can do this with computer systems these days, the manipulation systems. A few of them we saw also as part of this course. So this is the crux of linear algebra. You should be very comfortable with all the notions involved here. Okay. So once we got a good idea of the basic notion of operators, we added this very, very important notion of inner product into the mix. Inner product is this very elegant way of taking two vectors and doing a mapping of them into a scalar, and that scalar value tells you something about how the two vectors are related. There are some specific ways in which you can think about it. For instance, if the inner product goes to 0, then these two vectors are sort of orthogonal, perpendicular to each other. If they are not 0, if the extent to which it can be related to the angle and all that. So there's a lot of intuition based on just that one value in understanding the relationship between two vectors. Okay, so this inner product ends up providing wonderful structure to this world of bases and operators and everything. Okay, so the first thing you can do is you get this notion of norm and angle from inner product. Distance, you start thinking of distance between two vectors using the norm. Okay, subtract the two vectors, take their norm, you get the distance, and the inner product gives you angles. So a lot of geometric ideas enter the picture in linear algebra once you bring in inner product. So the geometric intuition is extremely important. Okay, so there's this orthonormal basis which really changes so many things about how you think of vector coordinates. Once you have an orthonormal basis, the coordinates of a vector are very easy to find out. You just have to do inner product with the vector and you get the coordinates. They're very, very easy to work with. In particular, you start getting this notion of an adjoint of an operator. So this is a very important idea. With respect to an orthonormal basis, when you think of operator's matrix, adjoint is just the transpose, and otherwise also the operator adjoint and the operator itself share a lot of very important properties. The eigenvector, eigenvalue properties are particularly interesting, and when the adjoint and the operator have a special structure, then a lot of things simplify in terms of the structure of the overall operator. So in short, the inner product gives you a certain angle and a perspective to view linear algebra. It gives you the geometry, it gives you distance, it gives you angles, so many other things it provides. Adjoint, for instance, is a very, very important notion. Okay, so several problems you can solve very elegantly. One problem that we saw is if you have a subspace and if you have a vector outside the subspace, what is the closest vector in the subspace to the vector outside it? So that was a crucial idea that we saw, and that is obtained by this orthogonal projection. Notice how the geometry extends beautifully, right? So the basic geometry that we do, if you have a line, a point away from it, how do you find the closest point in the line? You drop a perpendicular, you get it. So this is a simple geometric picture. Now this extends to all of vector spaces, inner product spaces, right? So when you have a subspace, you have a vector outside it, you just orthogonally project, and then that projection has a lot of properties, and like it's closest, everything else is orthogonal to it, etc. And we saw all those very interesting properties. So using linear algebra, this elegant solution to the closest vector in a subspace problem has tremendous applications. We've seen quite a bit of it already. Okay, so this notion of an inner product and adjoint also gives you a way to classify operators. Okay, otherwise there's a zoo of operators, so many different types. What are the different types of these operators? So if the adjoint and the operator are the same, you get self-adjoint operators. They are really, really simple, isn't it? They have a full set of eigenvectors, they're diagonalizable, they have real eigenvalues. So if you have a need for that, you use self-adjoint. And we also saw a lot of applications where naturally the operator and its transpose operator and its adjoint are the same, right? Symmetry comes sort of naturally into the problem, and you use that symmetry, you use the diagonalization from there, and then proceed. A slight generalization of self-adjoint is normal matrices. Normal matrices, they commute with their adjoint. A T star equals T star T. So both of them commute, and that itself gives a lot of nice eigenvalue, eigenvector structure, except that the real eigenvalues property is lost, but there is a full set of eigenvectors. It's diagonalizable with respect to an orthonormal basis. And then when you look at this unitary matrices, they're also very special, isn't it? If you have the columns of a matrix being orthonormal basis, then you have a unitary matrix with you, and a unitary operator representing an operator is just represented by that matrix, right? So those are very, very special. So when you have an orthonormal basis, multiplying a vector with them is like the matrix representation, the coordinate representation of that vector. They're very, very powerful. So in particular, when you have diagonalization with respect to an orthonormal basis, the operator is really, really simple, isn't it? So what happens to an operator? It may do a lot of mixing of the coordinates otherwise, but what an operator which has an orthonormal basis of eigenvectors does is, there are a certain coordinates. I mean, you change the coordinates to some other rotated version, and then all your complicated operator is doing is scaling coordinates, right? So it's diagonal in that orthonormal basis. So that's very nice. We also saw positive operators very briefly, just to get an idea of what these things are. So this classification of operators is also very, very important. So lots of linear algebraic results that work for these special classified operators. Okay, and a whole bunch of methods we saw in this area as well, right? The Gram-Schmidt orthonormalization process is a central method. Once you have an inner product, and you can take a linearly independent set of vectors and then convert them into an orthonormal basis which spans the same set, right? So it's a very powerful idea, and that leads to every other method, like projection, a lot of diagonalization ideas. All of that is important, and you need to pick up a certain skill with that joint, right? So matrix and that joint, what they do together, what are their properties together, that also is very, very important. Okay, so these three ideas, the basic notion of vector, vector spaces, subspaces, linear dependence, independence, Gaussian elimination, all of that is the first part. Next comes the operator, linear transformation, eigenvalues, eigenvectors, the four fundamental subspaces, all of that, and then the inner product space. Okay, the inner products and the projections that they bring in, all the classification of operators based on that, the Gram-Schmidt process, the orthonormal basis, all of these ideas are extremely, extremely important. The very final part of the course was, okay, so before I go there, we saw a whole bunch of applications along the way. Okay, so let me just quickly walk you through what these applications are, right? We saw the first sort of application is solving DC circuits. You might have already seen that linear equations play a very central role in solving DC circuits. Even you can even do AC steady state solutions. There the complex field will come in. Again, you will have simple linear equations to deal with. So if you go a little bit further, look at matrices and matrix powers, there are a lot of control system problems where stability involves the idea of eigenvalues. So if you saw that when you raise a matrix to higher and higher power, and if it's diagonalizable, then the eigenvalues really control what happens to the matrix power. If the eigenvalues are all below 1, then eventually all the powers go to 0, right, matrix power. But if the eigenvalue is above 1, the matrix starts blowing up. We saw some examples of that. So this occurs a lot in feedback-based systems, right? So something happens in iterative systems, same, repeatedly if you apply a matrix to an operator, to a vector, the powers of a matrix naturally come, and that happens in iterative systems, in feedback control systems. A lot of applications use that. So the idea of matrix powers being associated with eigenvalue powers is central to a lot of applications. There we saw a little bit of that, maybe not too much. Okay, and then we saw a lot of signal processing applications, right, where basic filtering, the digital convolution, discrete time convolution process being represented by circulant matrices, and the fact that circulant matrices are normal, and once they are normal, we know that there is a full set of eigenvector, orthonormal eigenvector basis, but in particular for the circulant matrices, the Fourier basis ends up being that orthonormal basis. From there we can define this DFT, which is the discrete time Fourier transform, which gives you a very simple view of what the circulant matrix is doing, and that leads to a lot of advantages in signal processing. As you study more, you will see this quite a bit in electronic systems. Okay, we saw conics. Conics was a very nice application of quadratic forms, how just the two-dimensional conic, and even a generalization of it. You can use quadratic forms, and you naturally get a symmetric matrix involved there, and the diagonalization of that symmetric matrix leads to a lot of simplification to the geometry of quadratic forms and conics. We saw oscillating systems, right? So differential equations, coupled differential equations, how a symmetric matrix enters the picture there, and how the diagonalization of that symmetric matrix gives you a decoupling of the coupled differential equation, and you can solve it. So you get fundamental different modes of oscillations when different systems combine together. So now this idea is used quite extensively in science and engineering as well. So all of these are very powerful ideas. They show up again and again in so many systems. We saw statistics. Statistics had some covariance and correlation matrices. Once again, symmetry came in, positive definite matrices came in, and you could use them the matrices played a central role in understanding correlation between different data sets. We saw graph theory very briefly, how the adjacency matrices are symmetric, and how the eigenvalue properties of adjacency matrices can help you infer properties like when the graph is bipartite, okay, which otherwise sounds like a slightly more difficult problem. You're able to do that very conveniently with the idea of linear algebra. Just look at this picture, right? So it's still not at over, and we've only scraped the surface. It's not possible to cover all possible applications, but hopefully the breadth of these applications gives you a sense, the sense of the vital role linear algebra plays in all of science and engineering. Every single model will have a matrix and a vector view of what is going on. Okay, so you can go look at it. If you don't believe me, you'll see it will come again and again and again. Okay, so finally, towards the very end, we sort of concluded by looking at infinite dimensional vector spaces. So far, we saw finite dimensional vector spaces. These are sort of easier to understand, but when you move towards infinite dimensional vector spaces, it allows you the ability to think of functions as vectors. Right, f of t, g of t, all of these guys, functions of time, which we think of as signals, they can be thought of as vectors. You can add them, you can scale them, they are vectors, but they also have an inner product. You use the integration idea, and if you integrate the product of the functions, you get an inner product, which means you get a norm, you get angles, you get geometry, right? So once you have all of that, it's very, very, very powerful. So this view also we saw. So it turns out many aspects from finite dimension carry over, except that you have to start worrying about convergence. Okay, so provided some convergence happens of some sort, just watch out for that, because these are infinite number of things adding, so some convergence has to happen. So as long as convergence happens, you're okay. So ideas like Gram-Schmidt carry over, the orthonormal basis notion carries over. At least you can think of an orthonormal basis and think of the span of that. Idea of projection carries over. When projection carries over, you can solve these elegant subspace, closest vector and subspace problems, and that gives you this notion of polynomial approximation, that gives you Fourier series, and how Fourier series for functions are obtained. So these are nice extensions. Once again, the idea of infinite dimensional vector spaces is very vast. There's lots of things you have to study. We just saw an introduction so that we can think of signals in electronic systems and functions of one variables also as vectors, and do some some of the methods that we did in linear algebra you can carry over here. So that again shows you the power of the linear algebraic thinking in some sense, right? So it's very, very powerful. Okay, so in conclusion, I really hope you've enjoyed learning and understanding the methods and the power of linear algebra and how widely it's applicable everywhere. And it's not just the joy of learning here. In fact, people have used ideas of linear algebra to build really huge companies which make billions and billions of dollars. So there's a lot of money value associated with it. Here is a paper. Google's famous PageRank algorithm uses strong linear algebra concepts and its good understanding of linear algebra it's exactly what resulted in something like the PageRank algorithm. So this is very nice paper. It says $25 billion eigenvector. Okay, so it's very nice when you relate math with money, right? And you get these kind of wonderful papers. Hopefully this inspires you to improve your conceptual understanding of algebra, linear algebra, and then use it somewhere, and maybe, who knows, you can be a billionaire as well. Okay, so let me conclude by wishing you the very best of learning and using of linear algebra in the rest of your career. Thank you very much.